We are watching a rapid transition in software development. The industry is moving from simple code assistants to fully autonomous software engineering agents. These systems independently plan features, write logic, and execute multi-file pull requests. This capability puts immense pressure on engineering leaders. They are pushed to adopt these agents to cut costs and increase output, while simultaneously facing intense pushback from their own senior developers. This line chart shows the disconnect. As marketing claims about autonomous AI success shoot upward, the trust from the senior engineering staff tasked with managing it steadily declines. The frustration comes from the results on the ground. Codebases are flooding with what the developer community calls vibe-coded technical debt, code that looks correct at a glance but lacks structural integrity. The objective truth is that these agents rarely fail at writing syntax. They fail because they cannot navigate the architectural complexity and undocumented quirks of real-world enterprise systems. Every autonomous deployment represents a strict architectural trade-off that immediately stresses existing infrastructure. To understand why, look at the first major deployment model, GitHub integrated automation tools like Sweep. These tools live directly in your version control ecosystem. You install a repository-level app and define your coding standards in a simple YAML configuration file. A single Jira ticket is automatically converted into a draft pull request inside the GitHub repository without human intervention. When applied across a distributed team managing dozens of repositories, velocity scales exponentially. Jira tickets flood the system, instantly generating dozens of draft PRs. That sheer volume creates a massive bottleneck. The work doesn't disappear, it simply piles up at the human code review stage. Reviewing AI-generated code requires a senior developer to constantly switch mental contexts to verify the logic. That review process often eats up the time saved by the initial automation. Without strictly constrained continuous integration and deployment pipelines, this model simply trades upfront coding time for exhausting high-volume review time. The second model tackles deep end-to-end development tasks using enterprise-ready autonomous environments, like Devin or OpenHands. These require heavy infrastructure inputs. You need dedicated egress routes, internal DNS resolution, and minimum compute resources just to get them running. This architecture map illustrates the core operational benefit: an AI agent isolated within a secure virtual private cloud boundary. It maintains a persistent state, allowing it to safely interact with external services and autonomously debug cross-service issues for hours. But drop this agent onto a 10-year-old legacy monolith, and it often fails catastrophe. Older codebases are full of circular dependencies. When the agent encounters these undocumented, tangled service boundaries, its autonomous decision-making loops get confused. If an agent modifies a payment API that 47 other services depend on without understanding the undocumented backwards compatibility requirements, it will break production. Enterprise agents offer immense autonomous power, but they demand perfectly documented, rigid service boundaries to avoid cascading systemic failures. The third model is multi-agent orchestration. Frameworks like MetaGPT simulate an entire software development company. Instead of one agent doing everything, the architecture assigns distinct specialized roles to different large language models. One acts as the product manager, another as the architect, and others as engineers. This structure creates rigid standard operating procedures. The agents collaborate and debate, preventing ad hoc destructive code changes. However, simulating a whole team introduces massive operational overhead. That deliberative planning process is completely useless if you need an urgent, real-time patch for a production incident. This quadrant chart plots system complexity against agent success rates. Across all three of these deployment models, you hit a systemic slop factor, a steep drop in success the moment test coverage falls below 30%. This is the danger of the vibe coding illusion. An agent will confidently force a solution that compiles and works locally, while silently breaking hidden dependencies in the live production environment. When that happens, human engineers are forced to step in and reverse engineer complex, confidently written, but flawed AI logic. In low-coverage codebases, autonomous agents create a labor shift. Engineers spend their time untangling dangerous knowledge debt rather than writing original code. AI agents aggressively amplify the existing need for engineering rigor. Before an agent can succeed, you need 3 non-negotiable prerequisites: pristine documentation, rigid test coverage, and strictly enforced service boundaries. You have to distinguish between the perceived dependencies written in your documentation and the actual runtime dependencies executing in your live environment. Before granting an agent write access, you must use runtime analysis tools to map how your services actually interact under load. Preparing a complex codebase for an AI agent is often significantly more work than the actual coding tasks the agent is meant to solve. This decision tree flowchart maps out how to choose your path based on your specific constraints. We start with startups and solo developers working on greenfield projects with low architectural debt. If you fall into this category, adopt GitHub integrated tools to maximize feature velocity, accepting minor early technical debt. For enterprise teams operating at scale with strict security requirements, the path shifts toward environments like Devin or Copilot Enterprise. Leaders must accept that utilizing VPC isolation and SOC 2 compliance requires weeks of upfront dependency mapping before safely refactoring core code. Finally, teams managing legacy systems with low test coverage and tangled architectures should stick to Copilot assistance. For these environments, the effort required to untangle an autonomous agent's mistakes vastly outweighs the time saved by generating the code in the first place. Trying to force a high autonomy agent into a low coverage legacy system is the fastest path to unmanageable technical debt. Success requires matching the agent's architecture to your specific infrastructure constraints and risk tolerance.